Hello. So thanks for having me here, and thanks for staying for this last session. I'm John Liagouris, and today I'm going to talk about some work I've been doing the last 3 years on real-time data center analytics. So the motivation behind this work is that existing data centers are heavily instrumented to log almost every interaction between the different system components at almost all layers of the software and the hardware stack. And these traces are generated as streams while the systems are running. However, existing tracing systems, trace analysis systems, either support only offline processing, or they rely on specialized in-house solutions to handle the streaming nature of the events. Our work in this case takes a different path. We argue that tracing systems can benefit tremendously from some recent advances in streaming data flow engines that can ingest these streams at scale and process the data in real time. So in the big picture you see here, imagine the system on the right as a part of the data center that is connected to the existing logging pipelines and helps administrators understand what's going on with the rest of the data center in real time. So, as I already said, the data center stack is heavily instrumented and generates massive amounts of logs. However, all these individual logs, the event, the stack traces, the telemetry data, tell only a very small part of the story. And actually, in order to make sense of performance at the scale of a data center, we need to track the lineage and the dependencies of these events. So in the following, I'm going to give you a very high-level overview of two works I've been doing in this direction. The first line of work is about trace tree reconstruction. So in this setting, we have applications running in the data center. These applications are instrumented. They generate distributed streams of events. Each event has a different type and comes with a set of metadata, some context, like the metadata you see on the left. And the goal here is to reconstruct the end-to-end traces from the individual events based on the metadata of the events. Why do we want to do that? Well, because trace trees underpin many different diagnostic tasks, root cause analysis tasks, performance analysis tasks, auditing, even billing, so they are essential to the operation of the data center. So we implemented the trace tree reconstruction as a library on top of a streaming data flow system written in Rust. In this work, we used Timely data flow. And we evaluated our system with data from a real data center provided by our industry partners. What you see here on top is the high-level overview of this data center. This is heavily instrumented, so we have logs from middleware, application servers, distributed file systems. And the logs here are spread across 42 log servers. This amounts to more than 1,000 log streams, with a mean total rate of approximately 1.3 million events per second. And in this setting, our system could construct the complete trace trees in real time and keep up with the workload using only a single commodity machine with 8 cores. But besides the actual trace tree reconstruction, an additional benefit of using streaming data flows for trace analysis is that we can compose different analytics easily and still meet the real-time requirements. So what you see here is the latency of two different analytic tasks on the stream of the reconstructed trace trees. And this latency here actually includes the latency to construct the trace trees. So the task on the left does a simple clustering. It clusters the trace trees based on their structure, whereas the task on the right computes the top 5 most frequently communicating services across all constructed trace trees. This library is open source, and you can find more information in our GitHub repo. Now, the second line of work I would like to talk about is related to online critical path analysis. And the setting here is a bit different than the previous. So in this case, we consider long-running services that execute tasks and exchange messages with other services. So the timeline you see here is an abstract representation of a distributed service execution. Each horizontal line corresponds to a service that executes tasks, and the dashed arrows are actually messages exchanged between services. Now, to motivate the need for accurate performance profiling in this setting, let's say that you want to optimize the end-to-end latency of the distributed execution. And you use conventional profiling in order to identify bottlenecks. So in this hypothetical example, if you use a conventional profiler, then the profiler would point to task A as the most time-consuming task because it has the longest duration in this particular part of the execution. However, if you try to optimize task A, in this case, then you will see no reduction in the end-to-end latency of the execution. And the reason is straightforward. In this hypothetical example, task A was not critical for the performance of the execution. Services 1 and 3 were actually blocked. They were already waiting for service 2 in order to proceed with execution. So the takeaway message here is that conventional profiling can be significantly misleading when we're talking about distributed execution. And in fact, what we need to do in order to make sense of performance is to compute the critical path dependencies of the service requests. If we have the critical path, then we have a set of tasks which are good candidates for optimization. However, computing the critical path for thousands of services in an online fashion is a very challenging task. So to address this problem, we implemented another library on top of the same streaming data flow system. We call this library SNAILTRAIL, and it works as follows. It takes streams of events, traces, from the instrumented systems. It slices these streams into time windows, snapshots, applies some graph-based metrics, critical path-based metrics on top of these snapshots online, and generates some very nice performance summaries. So with SNAILTRAIL, what you can do is you can generate profiling summaries like the one you see here on the left. This is a summary for a Spark job that shows the contribution of two activities to the critical path of the computation, processing and scheduling. And as you can see here, clearly the scheduler is a bottleneck. And this was actually a known issue in Spark that was later addressed in OSDI paper in 2017. But the cool thing here is that we were able to identify this problem. We were able to visualize this to the user while the system was running. So the x-axis here is the elapsed time of the execution. And just for reference, in this slide on the right, I have the same profiling summary for the same job when using conventional profiling. And as you can see, the two summaries are quite different. And the reason is, as I said, that conventional profiling completely ignores critical path dependencies and tends to underestimate the contribution of tasks and activities to the critical path of a distributed execution. So this is ongoing work. You can find more information in our GitHub repo. I'm actually working with a couple of students on integrating SNAILTRAIL with OpenShift so that we can process logs from Mass Open Cloud in real time. If you're interested, please come talk to me. Thanks.
I don't know how to close this on the Mac. Do I just move it around or?
Let me get that. No, we can get that off for you. That's weird. Work. Can you check if that worked? Oh, it's still showing. Is there any way you can turn this off? I don't know why it's not.
Maybe if you click present again, if the other thing is has disappeared now.
It's right here. Was that it? Is it right here? That's causing the problem? Okay, so it should be fine now. Let's try that.
Okay.
All right, sorry about that.
Hello everyone, I'm Emre, and today I'll talk about our just-in-time framework for tracing distributed applications. So debugging distributed systems is very challenging because of the difficulty of knowing where the problem is coming from. It could be in one of the many components that comprise the system. It could be in one of the several stack levels that the components are hosted on, like the virtual machine or the hypervisor or the kernel. And it could also just be like an emergent behavior that arises from these intercomponent relations that only happens when you put everything together and run it and scale. So today's debugging methods rely on instrumentation points to find out where the problem is coming from, like John has talked about. The problem with this is that different problems benefit from different instrumentation points. And if you want to instrument everything to catch any possible problem that may happen in the future, then you will be just collecting instrumentation data with your system instead of doing useful work. So today, what developers do is they start with a bare minimal amount of instrumentation in the running system, and then when a problem happens, they try to kind of guess where the problem is coming from. And if you can't find the problem, then you inject more instrumentation, you run it again, and then you kind of try to narrow down the source of the problem just over and over again with this manual iterative approach. So our research question is whether we can create a continuously running instrumentation framework for production distributed systems that will automatically explore these instrumentation choices across the different stack levels for a newly observed performance problem. The key insight that we use to realize this system is that performance variation indicates where we need more instrumentation. So on this graph, you see a request. That's basically the nodes of this graph represent events happening across systems, and the edges represent happens before relationships, and then the time flows like to the right, and the hierarchy of the system is to the bottom. And this is a read request from storage. So it starts at the client, then goes through the load balancer, and then does some operations at the backend services, and then returns to the client. Now, if you have a lot of read requests in a system, and they are expected to perform similarly, then they are expected to perform similarly. And if we trace a bunch of these read requests and we compare their traces, if one of them, for example, takes a lot longer than the other ones, then this performance variation would be a good indicator of where we need more instrumentation. So here you can see the read component is taking a variable amount of time between requests, and we can actually add more instrumentation to the read component automatically without relying on the manual analysis of developers. The key enabler that lets us get these graphs from distributed systems is workflow-centric tracing, and it works by propagating a request ID with the request and recording events accordingly. The granularity of the data that's available to us is determined by the instrumentation that's already in the system. So the vision of Pythia is I'll just go over it now, but basically it's a system that first gathers these workflow skeletons in the form of graphs and extracts critical paths from them and groups them based on performance expectation. Then we identify which of these groups have high performance variation, and we localize the performance variation within the group. After that, we can enable and disable additional instrumentation and start the cycle again to collect new data and enable more instrumentation. Instead of performance variation, we could also look at consistently slow groups as a second signature of performance problems. So today I'll talk about the more challenging aspects of this framework, which are the grouping, the localization of problems, and also deciding what to enable next. So the grouping basically is grouping workflows that are expected to perform similarly. And this expectation depends on the application that's being debugged. But a generally applicable expectation that we found is that the requests that are of the same type that access the same distributed system components generally should perform similarly. But additional application-specific details could be also incorporated. For example, if you're a storage system, maybe you could say read requests that are also of similar size should perform similarly. Yeah, so for example, here's a group of read requests and a group of, for example, authentication requests. And the second challenge of this framework is the localization. So the localization is in two stages. First of them is among the groups that we have collected, and the other ones within the groups. And to localize something, we need to order these groups based on a metric, which is basically how we quantify performance variation. There are multiple metrics that we can use to measure variation, like variance or standard deviation is one thing. Another one is coefficient of variance, which is the standard deviation divided by the mean. It's intuitive because if something has a smaller mean compared to the standard deviation, it would make more sense to prioritize exploring that. But in practice, actually, if you have a very small mean of some edges, then this could result in a very high coefficient of variance. And we don't really want to explore some things that take microseconds. So it's a trade-off. And we could also look at multimodality as a signal of problems. So if we have a distribution that has multiple modes, we could maybe enable something that would explain why some of them take longer than the other ones. And the third challenge is deciding what to enable after we have localized the problem. For this, Pythia uses a search space and search strategies. The search space is basically how we represent all of the instrumentation that Pythia can control. And the search strategies are ways to traverse this search space. So the search space helps us find the relevant next trace point after the problem is narrowed down. We want the search space to be quick to access and compact while also limiting our search to a relevant set of trace points. And the search strategies, we also want them to quickly converge on problems and also keep the instrumentation overhead low by not enabling a lot of things. So there are many possible options for the search strategies. So in our full design, we have a pluggable search strategy, which for maybe each distributed application, you could devise your own search strategy. So after you enable more instrumentation, like I said, you come to the beginning and you collect more instrumentation data to keep going with the cycle. So I'll go over just a little bit of experiments. Here's one example where we validate our approach using OpenStack. OpenStack is basically an open source platform for clouds. It's used in MOC. And here's a bunch of requests to OpenStack and their corresponding latencies. So in the top, you see the server create request group actually has a very high variance and also very high mean latency. And compared to all of the other requests like floating IP allocation or listing the servers, this one definitely seems to be the problematic group. So Pythia would, in the localization step, in the grouping step, out of all of the requests, Pythia would group the requests into these rows that you see here. And in the localization step, it would focus on the server create group. And we actually run Pythia online on our own OpenStack, where Pythia then localizes the variation into a semaphore in the server create request. And after enabling the instrumentation in that semaphore, which reports the number of requests that are waiting on the semaphore, we see that the request latency is grouped into 3 different groups, where the fastest one has nobody waiting on the semaphore, second fastest one has like 1 to 3, and the other one has 4 and more. So the takeaway from this is that Pythia's approach can actually identify the instrumentation that's needed to debug this problem, and we have also, so that's the takeaway. And it's, in conclusion, it's very difficult to debug distributed systems, and automating instrumentation choice is a promising solution to overcome this difficulty and help debug distributed systems. Thank you.
Hello, everyone. My name is Mania, and I'm a PhD student at Northeastern University. Today, I'm going to talk about workflow motif, an abstraction for debugging distributed system. And this is a joint work with Northeastern, BU, Red Hat, State Street, and Tufts University. I want to start the talk with constructing how we build distributed systems versus how we debug them. Today, distributed systems are amazingly large scale and complex, and the way we are able to build this complex distributed system is by leveraging abstractions. Abstractions allow developers to build really complex distributed systems out of simpler building blocks. And how they do is that they mitigate the amount of complexity that developers should deal with. Example of abstractions are the APIs that we are using, or the libraries that we are using for building distributed systems, or it could be, for example, using smaller building blocks to build larger distributed systems. Another example of abstractions are the data center architecture that consists of different layers of abstractions. So these abstractions allows developers to hide the complexity of the underlying layer and build them more easily. So in contrast, when we debug distributed system, we usually have no abstraction, and we usually have less sophisticated abstraction. In fact, the de facto approach to debug this distributed system is to use no abstraction whatsoever. We use raw logs that we might take from the system, or we might use raw traces that shows the graph of distributed system activity, and which shows how distributed systems perform a request. This extreme mismatch between how we build distributed systems versus how we debug them can be challenging and could cause performance debugging and debugging distributed system very hard. What we observed is that traces shows repetitive pattern within and across many requests. And these patterns are repetitive building blocks of how request is executed through the system and how distributed systems behave. We believe that by understanding the performance behavior of this pattern, we are able to make engineers to discuss about the performance characteristics and their expectations of the system. And it could address a wide range of tasks. In this work, we are exploring the utility of extracting these repetitive patterns from the traces of distributed system, and we build a novel abstraction for diagnosis tool called workflow motif. Workflow motif describes frequent processing patterns in the workflow of how requests are executed through the system along with their performance characteristics. And these workflow motifs are essentially the building blocks of distributed application runtime behavior. Different permutations of these workflow motifs are largely make up how request is processed by the system. An example of such processing patterns are, for example, the work done by distributed system to leader election. And how workflow motif helps engineers is by hiding the complexity of the underlying layer and eliminating the irrelevant problems to a given problem. I want to explain the workflow motif using an example from a workflow of write request to a distributed storage system called Ceph. And how this work is that workflow motif can find two types of motifs here. The top one shows the work done for metadata operation, and then the bottom one shows the frequent pattern that is observed for the trivial replication to the data nodes, to the OSD nodes. And then we discussed that workflow motifs are composable, which means that larger workflow motifs consist of smaller workflow motifs, and also workflow motifs consist of the performance behaviors of those motifs. This allows us to discuss the performance behavior of each frequent processing pattern individually instead of looking at the entire trace and discuss the entire trace at the same time. The key enabler for identifying workflow motif is end-to-end tracing tools or workflow tracing tools. And here is the basic explanation of how this workflow tracing tool works. This figure shows the deployment of distributed storage system along with a table store on top of that and the client application that access to the table store. So to capture the workflow-centric tracing infrastructure use trace points, and trace points are embedded within the distributed services code base. These trace points are added either dynamically to the code or they are embedded into the common libraries or could be enabled or disabled through the execution of the system. And these trace points have unique names and record the arbitrary low-level parameters of the system, such as CPU usage or disk usage or, for example, the queue length. They could capture different type of parameters and configuration parameters of the system. And then when a request is executing, tracing infrastructure propagates some context. We call them metadata propagation along with the request. And this allows the distributed tracing tools to restruct the behavior of the system and build the workflow of how request is processed through the system. For example, on the right side, you can see the workflow of writing to the HDFS, which is a distributed storage system. And our approach is to build workflow motifs by using frequent subgraph mining tools. Frequent subgraph mining tools are finding frequent patterns within a large corpus of traces and a large corpus of graphs. And these tools use a metric called support level for defining the frequency or the interesting frequent patterns. And these algorithms are widely used in DNA matching or in chemistry component, detecting similarities in chemical components. And they are usually expensive, both in terms of storage and in terms of performance. So our goal here is to adapt these tools to our specific domain problem. Here is software components for building workflow motifs. Underneath, you can see this distributed system. For example, here is a distributed storage system, and then on top of that, there is the end-to-end tracing infrastructure, which captures the workflow. Workflow motifs retrieves traces from the trace database, and then using frequent subgraph mining tools to extract the frequent patterns and filter the frequent patterns based on the required specification of the user. And then we enable querying to this corpus of motifs, or we enable users to annotate those motifs. And different use cases could be contrasting different execution traces or identifying anomalies among them. We can use them for identifying optimization. For example, we can look at the traces, we can look at the workflow motifs that has the largest performance variation and then choose them for optimization. Or we can use it for application comprehension. Now I want to discuss how we want to use frequent subgraph mining tools to fit them to our requirement. And I want to discuss our requirement first. The first requirement is that workflow motifs should preserve the work that is done, the ordering of the work that is done in the system. This means that in some of the traces, we observed that there is the similar work that is done through the workflow of the system, but the ordering is different. And in some cases, some of them are frequent and some of them are not frequent. So we expect our frequent pattern mining tools to be able to detect this behavior. The second thing is that workflow motifs are frequent across and within traces. This means that there are some frequent patterns that are happening among a large subset of traces, but few number of times, and there are some frequent patterns that are happening within a smaller number of traces, but many, many times within those smaller set. So our frequent subgraph mining tools should be able to capture both of these behaviors. And the third characteristic is that we have to add the performance characteristic metrics to the frequent subgraph mining tools to be able to report it as an output of the workflow motifs. So we go over 5 frequent subgraph mining tools. We go over FSG, which is a joint-based method, which means that it's start from 2 nodes and then add another node and expand the graph as much as possible. It doesn't consider edge order, or it doesn't consider it doesn't preserve the ordering, so it is not point of our interest. That's and also it is looking for graphs within a corpus of the traces, and it doesn't look for across traces. The second one is Gaston, which is a pattern growth, and it starts from a node and expand that node as much as possible and build the largest graph that it could. The good thing about Gaston is that it starts from passes, and then it looks for trees, and then it looks for graph, which makes it more practical in our approach. Unfortunately, it doesn't support edge order, and it looks for frequent patterns across many graphs. We look at Grammy, which is based on FSG, and but it enables lossy frequent patterns, which means that you can find frequent patterns that are not exactly matching together, but with some differences, we can consider them as similar frequent patterns. And then Arabesque is a distributed approach that currently does not support the edge ordering, but it is based on the Grammy, and it is a distributed model, which is helpful for our having a scalable approach. And ASAP provides sampling within the frequent subgraph mining algorithm, which means that it doesn't require to find the entire graphs, and it only looks for a subset of them. Now I want to discuss the preliminary results we got from HDFS traces. We captured some, we ran some benchmark on top of HDFS, and we captured some traces. And we ran Gaston on top of those traces. And we were able to capture 2 motifs that were interesting for us. The left one shows the motif for reading from network, reading data from the network, and the one on the right shows the reading a block of data from the within the data node. And we were able to annotate each of these traces with the with their runtime behavior and their performance characteristics. So now I want to go over some of the use cases of this tool. So one of them is compare and contrast different workflows, which means that we can compare and contrast different workflows, identify their similarities, and identify where they are different. We can use it for anomaly detection by filtering the frequent patterns and only looking at the non-frequent patterns. And also we can use it to improve slow performance by, for example, finding optimization points for optimizing the system. And in summary, we believe that abstractions are powerful tools for building distributed systems, and we want to enable them for debugging distributed systems. We introduced workflow motif, which is a novel abstraction for debugging and diagnosis in distributed systems. And our approach is to building workflow motifs using frequent subgraph mining tools. I'm done.
Okay. Hi, everybody. My name is Vasiliki Kalavri. I recently joined Boston University as an assistant professor at the computer science department, and I work in the area of stream processing, large-scale big data processing systems. So today, I want to give a very high-level overview of my recent research, but also mention a few trends that I see in the area and a few opportunities for further research. So it is a very exciting time to be working in stream processing. Over the past few years, stream processing systems have established themselves as a major data analytics technique in all kinds of businesses. All major cloud providers have some sort of streaming as a managed service. And at the same time, we see more and more digital companies that realize that stream processing is not just for their business analytics team, but it's something that is useful to the whole company. So we see more and more companies which build their own in-house solutions for streaming. And just to mention a few, Uber Engineering has recently released Athena X. Netflix has built Keystone, and Facebook has built a bunch of tools for stream processing. Now, I would like to mention a few applications. So John already mentioned like using stream processing to monitor large systems like large data centers, but their use cases span even more areas. I will just mention two of them. So one is traffic light adjustment in real time and really city planning. This screenshot is from Alibaba City Brain. This is a streaming application that is currently monitoring the traffic in the city of Hangzhou in China to clear paths for emergency vehicles and to provide scheduling information to users of public transport. Another really quite impressive application is the use of streaming in NASA's Deep Space Network, where they use stream processing to analyze data from satellites and spaceships and really make sure that everything is working as it should in space. So this is all really exciting, right? The really impressive thing about this area is that most of these applications and most of these tools are built on top of open source software. So a lot of these systems are currently under the Apache Software Foundation, so you might recognize some of them. I personally work with Apache Flink, which is a pink squirrel, the cutest logo of all. But you know, systems as Kafka, Storm, Spark, Beam, and so on. So, you know, there's a ton of tools out there, and you might be wondering, okay, how do I choose the right one? So these tools are just superficially different. So in fact, they're very similar in the way they operate. So they all rely on the data flow programming model and execution model. So when you write a Flink job or a Spark job or a Storm job, basically what happens underneath is that your program is translated into a logical query plan, where the nodes in this graph are transformations on streams, and the edges between nodes are data dependencies, where, for example, if you wanted to continuously analyze a stream of tweets, you could build a data flow like the one shown on the slide, where one operator would read continuously tweets from a source, push those tweets down to an operator that extracts hashtags, and then this operator would continuously push the hashtags to another operator that counts the hashtags continuously, and so on. Now, in order to scale, these systems translate the logic data flow into a query plan, a physical data flow that leverages data parallelism to process large streams. So, in fact, every operator is translated into multiple instances that operate in parallel on disjoint partitions of the input stream, right? So, for example, here, the extract hashtags becomes 2 parallel operators, and the count topics becomes 4 parallel operators. These instances are then mapped to physical workers or threads, and these are deployed on a cluster of machines. So the most common architecture for these systems is shared nothing commodity cluster of machines. Right. Another very important feature of stream processing systems is state. So any non-trivial streaming application maintains some kind of state, whether that is a rolling counter or an average, or whether it's a complex window, stream processing applications need to have state management capabilities. So you can imagine each of those operators in the data flow plan continuously having access to some sort of a key value store, and for every event that comes in, they possibly make an access to the key value store to read the current value of the state, then compute something, and then write it back, right? So, yeah, and then output the result. Right, so this is how these systems look in a very high-level way. And now I would like to talk about some of the challenges and basically some of the recent work I've been doing in this area. So as you might imagine, one of the biggest problems we have in stream processing is that, as opposed to databases, a streaming system does not have any control on the input rate or order of incoming data, right? So you might have spikes, the workload varies. So one long-standing question, really, in this area is how can we build systems that continuously satisfy quality of service while not wasting our resources, right? And the two main questions that come up here is the question of control, so when and how much to scale, and also how to effect a reconfiguration without bringing the whole system down. So when we started looking at this problem around 2 years ago, we found that most of the current systems rely on heuristic policies. So they observe metrics on the outside, and they rely on policies that are rule-based, and they're of the form, if CPU utilization exceeds some threshold, then scale out. And this causes like this oscillation behavior that you see here, because you don't really have a model to apply, right? And they also mostly apply stop and restart reconfiguration. So if you want to add workers or remove workers, you have to bring the whole system down. Instead, what we would like is accuracy, so no over or under provisioning, stability, so that we don't have this up and down, fast convergence, and safe migration. So our solution to that was instrumentation, so looking inside the system and extracting accurate metrics, and then building a model that relies on these metrics to provide accurate and fast scaling behavior. So we have a couple of papers on that. I'm happy to talk more later today. Right, the second challenge I would like to mention is state management. And as I said, most of these operators have and maintain state, right? And they have to access some kind of an embedded key value store. So how can we make streaming have low latency while at the same time supporting larger than memory state, right? So for example, if we take Apache Flink, Flink works with RocksDB, and if you run an experiment within memory state and a RocksDB state, you see this large overhead in your latency. That comes from various reasons, but one of them is, for example, serialization, deserialization in every access. So this is work in progress, but our idea here is to leverage the fact that streaming queries are long-running, so we write them once, and then they run for a long time, so we can learn the access patterns of different operators, and we can build key value stores or state stores that are tailored to the needs of each operator. So we call this workload-aware state management, and our early results are very promising. Right. So in the last part of the talk, I want to just mention a few trends that I see in the area, a few things that people are working on and I also find interesting. So the first one is using streaming for machine learning, and in particular, using streaming for model serving. So if you think of model serving, it's a streaming job, right? You can imagine the samples that you want to predict on or categorize as events coming in a streaming application. And since we have this nice state management, why not having the models inside the stream processor itself so we can avoid the RPCs? A lot of problems come up in this scenario. For example, how do we version, how do we do versioning and model management in the store? What would the store look like? Is it always better to actually do that or not? What are the latency trade-offs? And how can we guarantee the exactly ones semantics in this case? A second trend is serverless or stateful functions. So some people in the community have started talking about leveraging the streaming features and the infrastructure that we already have to deploy orchestration of functions on top. So imagining the function invocations as events, and then these operators that I said are connected in a data flow can run the functions, right? And then you can leverage the fault tolerance in state management and the elasticity of the stream processor to make this work. A lot of problems here as well. We're missing support for transactions, for example. We're missing support for querying the state from the outside. Yeah. And the final opportunity is really using stream processor as an enabler in other fields of science, and especially in fields of science where we don't have flat streams, but we have streams with correlations and dependencies. So like the monitoring data of a distributed streaming, a distributed system or a data center, or security traces and user interactions, let's say, in a large network. And there, we need to advance both the capabilities of the current systems, but also see how we can use the systems we have to enable new advances in these fields. So I find this very exciting as well, so happy to talk more about all of this. Thank you very much.
Thank you. Hi, everybody. Last MicroTalk for this workshop, so I'm gonna try to finish up before we all fall asleep. All right, yeah, my name is Alex Bulekov. I'm a PhD student here at Boston University. My advisor is Professor Manuel Agle. And I'm an intern at Red Hat, and I'm excited to present some of the work we're doing on hypervisor security. When the cloud came around, enabled all these companies to move a lot of their computing that was going on their individual clusters into the cloud. And one of the killer features for the cloud providers was that they could run computing workloads for these companies on the same hardware. And this really allowed cloud providers to drive down costs and enabled unprecedented scaling. And what allowed for this to happen is really the underlying technology, which are hypervisors and the virtual machines that they run. And the other thing that really allowed for the cloud to take off was the fact that these companies, they didn't really need to do too much to their computing workloads to move them to the cloud, because you could move whatever operating system you were already using and whatever applications you were already using, and usually with quite very few changes, you'd be up and running on the cloud. But as you can imagine, it's no simple task for the hypervisor to really provide this virtualization layer which allows you to run an existing operating system and an existing application. And there's some pretty tricky situations you can get into. So if you have, for example, a compromised virtual machine, whether the tenant it was malicious from the start, or maybe one of their applications got hacked and the virtual machine was taken over, what the worst case scenario for the cloud provider is for this infection to get outside of that individual virtual machine, compromise the underlying hypervisor, and maybe even access the other customers' data or virtual machines that are running on the same physical node. And so the security, well, before companies had a way to protect this one, they had their own data centers. They could just hire a security guard and put them in front of their data center. But now they had to, now the thing that's protecting these companies from each other who are often running running their workloads inside the same data center or even inside the same nodes is this interface, which is the virtualization interface or the virtual devices. And this is such a critical interface that we'd expect, the code to be perfect and there to be no bugs in there. But unfortunately, this isn't true, and there's bugs that are found every month, sometimes every week even. And every time one of these bugs shows up, it's a big wake-up call that we have all this software that we're putting a lot of trust into, and not just the cloud providers are trusting this, but also all of the people that are using shared infrastructure. And if we look at what the job of a hypervisor is, well, mainly one thing it has to do is it has to split up the computing resources, so the CPU, between all the virtual machines. And fortunately, a lot of the complexity of doing that was moved into the hardware around 15 years ago when all the major CPU vendors added support for virtualization. But we also have all of these other devices that virtual machines and operating systems typically rely on. And unfortunately, a lot of these devices are still implemented in hundreds of thousands of lines of C or C++ code. And as we know, this code often has bugs. And if we look at how operating systems and typically interact with these devices, there's three major interfaces. So on x86 machines, there's a 64K space of addressable I/O ports, which are dedicated to interfacing with devices. We also have memory mapped I/O, which are ranges inside main memory, which are mapped instead of to the DRAM, they're mapped to I/O operations. So maybe you'd have a range that's mapped to all the pixels on your video card. And then we also have direct memory access capable devices where basically the OS can write the address of some data located at some random location in memory via port I/O or MMIO to a device. Then the device will asynchronously, without the CPU's involvement, go ahead and fetch that data and do whatever operations it needs to do. And that allows really high throughput devices such as VirtIO or such as network devices to do their job without the CPU being constantly involved for every byte that needs to be sent on the network. And so our work, we implemented our work for the open source QEMU hypervisor. And if we look at how one of these bugs might be manifested inside QEMU, so if an attacker crafts a sequence of malicious port I/O and memory mapped I/O inputs, they could potentially break out of QEMU's virtual machine confinement and into the host. And our goal is to be able to find these malicious inputs before the attackers do. And the way we do that is using fuzzing. And from a mile-high view, I guess fuzzing is just a way to provide randomized inputs to virtual devices in hopes of triggering bugs so we can reproduce them and patch them. But as I mentioned previously, the input space for virtual devices is enormous. So even if we think about just RAM for a 64-bit machine, we're talking about exabytes of valid addresses. So how do we actually how do we reshape this input space in a way that the fuzzer can actually interact with all these devices in a meaningful way? Well, the first thing that we can do is we can actually leverage APIs that the hypervisor already provides to enumerate all of the regions that are directly mapped to I/O devices, such as through port I/O and through MMIO. And that takes care of that part of the equation. But then we also have the direct memory access part, which is data that can live anywhere in memory. And the way we deal with that is that we hook all virtual device accesses to DMA ranges, and when we see a device trying to access some data inside main memory, we populate that data just in time, so we don't have to worry about about figuring out a priori where is the DMA data gonna live. And so overall, I mean that was a very quick overview of like some of the techniques we use for our system, but we also need to worry about enabling all of the I/O mappings and then enumerating the space, and then finally in our fuzzing loop, we not only do we need to generate the various I/O patterns and interpret them into actual I/O actions and handle DMA just in time, we also need to reset the state of the virtual machine after each run to make sure that there's no state leaking in between different fuzzing runs. And so as I mentioned, we implemented this for QEMU, and thanks to the resources that are available at the MGH-PCC, we were able to fuzz hundreds of different QEMU configurations in parallel. And one thing that we look at, for example, is how the coverage, so how the amount of code that we run in QEMU increases over time. And we can even zoom in on individual source files and look at individual virtual devices and see what percentage of those virtual devices our fuzzer has covered. And we can zoom in even further and look at the individual lines and use this to basically make iterations on our fuzzing technique and see how we can further improve the coverage that our fuzzer achieves. And we've already found bugs in devices such as the VirtIO class of devices, the QEMU's serial device, the MegaRAID card, and there's a lot more on the way that we're still in the process of triaging and communicating to the developers. Our work is already upstreamed into QEMU, so other developers are free to use it and use our framework to implement their own types of fuzzers. And due to QEMU's popularity, it's not only used in software that we know and love, such as Overt and OpenStack, but there's stuff like Nutanix, Proxmox, and like all of these other systems that rely on QEMU. And because of our changes to QEMU, these systems are already safer. And in the future, we'd love to have something that already exists for the kernel, where for every crash that we find, we build an automatic reproducer program, and then as new code is added to QEMU, we can test against these reproducers to make sure that bugs, that they not only went away after the patch occurred, but they also didn't come back. And finally, we're also actively working on getting our code integrated into a continuous fuzzing service, which would allow for bugs to be caught inside QEMU before they ever even made it into an official release to make hypervisors safer than ever. And I'd like to give a big thank you to everybody who works with me at Red Hat. And if this work sounds interesting to you, here are my contact details, and I'd love to talk to you. Thanks.